Alright. So now we begin with the remainder of our Unit 4, which involves hypothesis testing. This is the other big application for the course. Here we're going to focus on our concepts, and in our remaining lectures we will do some hard examples. Before we can do examples, we have to set up and define what a hypothesis test even is. So with any kind of hypothesis, we have this guess as to what we think is true or might be the case, and we test it. If it's not the case, then we reject it and go with the opposite. If it is the case, then we collect more data and try again. This is why with a lot of scientific theories, one experiment can't confirm it, but one experiment can reject it, because if it's true, it should hold for nearly all of the experiments. Whereas if it's wrong, even one experiment can disprove it. Like with physics, you probably, if you did a physics lab, you probably had a lab where you investigated gravity and how it works with the acceleration of 9.8 meters per second squared downwards. Every time you run the experiment, you're always going to get an experimental value for the acceleration due to gravity as around 9.8 meters per second squared. You might have 9.81, you might have 9.79, but that's just due to a little bit of uncertainty and error just by virtue of the measurements. You have a little bit of a spread there, and we've talked about spread before in this class, variance and standard deviation. But regardless, your value is always going to be in the ballpark of 9.8. You're never going to get a value of 5. You're just not going to unless your whole lab is screwed up. Kind of like how if you're doing a poll of Georgia and you get 25% of the vote for Trump, you screwed up your poll. So for here, we basically have our hypothesis and then the opposite of it. We call both of these hypotheses, and our null hypothesis is our assumption that we're making about some population parameter. So for example, we might assume that Trump will get 50% of the vote, so 0.5. The alternative is just the opposite of the null. We denote the null as H0, which we also call H0. Like not N-O-T, but N-A-U-G-H-T. Our alternative hypothesis is HA. And for these hypotheses, you will define one of them, and then therefore the other one is the opposite of the one that you're defining. So if we have something that we're hoping to prove, we make that the alternative. You might say, hold on, why not make that the null? Just prove the null and stop. Well, as we recall with before, with the gravity example, if it's true, it will hold in all cases. That's why when you do the physics lab, you say the 9.8 we got lines up with what we expect. It doesn't confirm it. It lines up with what you expect. And the reason why is the null is the assumption we're making. If we're assuming that something is true, you don't necessarily prove it, because then that might be a self-fulfilling prophecy. For those of you that have done some more pure math involved courses, you'll know exactly what I'm talking about. That is, you can't assume something is true and then work there. If you assume that 1 plus 1 is 2, you can't say 1 plus 1 is 2, therefore 1 plus 1 is 2. It's not how it works. Now 1 plus 1 is 2. But if you wanted to show that 1 plus 1 isn't true, you gotta prove that. That's the general idea. If you have an idea or a hypothesis that goes against what we already think is true, that's what you're trying to prove. The onus is on you. So in this case, if we're hoping to prove that something else is true, we make that our alternative. Put another way, we might have some general consensus, maybe some sort of alleged common sense or conventional wisdom that you think is wrong, and so you want to disprove it. A lot of the pundits back in 2016 were convinced that Hillary Clinton couldn't possibly lose Wisconsin. So the conventional wisdom was that she would win Wisconsin, and so therefore you might go out to disprove that to be the case. So as some hard examples, let's suppose we know back in 2008 and 2012, Colorado was a close state. However, you might think it's no longer a close state. So therefore, you're challenging the assumption that Colorado is a close state. So our null hypothesis is that the proportion of people who might vote for Biden, or the Democrat, is 50%. And therefore, the alternative is the opposite of the null. So the alternative is that P is not 50. In this one, for that example, we wanted to challenge this assumption, and that allowed us to identify the null. Therefore, the alternative is the opposite. If you've got one of the hypotheses, it's very easy to get the other one because it's the opposite. Now, let's suppose we think that we got a professor who's being a stick in the mud and just failing the whole class. So here, we're trying to prove that this instructor is giving out grades that are too low. So, since we're trying to prove their grades are too low, we make that our alternative hypothesis. And therefore, the null hypothesis is that their grades aren't lower than the rest. Now you might say, well, why not just say equal? You can, but as a practical matter, you could include the greater than or equal to, because as you'll see a little bit later, the equal sign is always on the null. You will never have the equal sign onto the alternative, because equal inherently implies it's an assumption. The equal sign will always be with the null. And using our notation up here, our H0 and our HA, we can say for the Colorado example, our H0 was that P is 0.5, and therefore we can also say that our alternative, HA, is that P is not equal to 0.5. For the grades example, we can say the H0 is that the grades given by the instructor in question are at least the same as the grades from all instructors. And the alternative is that their grades are lower than the grades from all instructors. So, let's suppose we have our two hypotheses. And don't worry, we'll get into some practices of identifying the hypotheses. So, obviously, we do our test. We get one of two outcomes. We think the null is true, or we think it's false. If it's false, we say that we reject the null hypothesis. If it's true, then we say that we fail to reject the null hypothesis. Now, you might ask yourself, how come we say fail to reject instead of accept? Or alternatively, you might ask, how come we say we reject the null instead of we accept the alternative? Well, the alternative is the opposite of the null, so saying we reject the null is the same as saying we accept the alternative. So then the question is, why do we say fail to reject? The reason why is that we assumed it was true. You can't accept something that you assume. If you're assuming it and you use it being true to say that it's true, that's a logical fallacy. And the formal word of it is that this is the argument to ignorance fallacy. Something isn't true just because you didn't prove it to be false. That meant you couldn't prove it to be false with the data you have. Now, you might ask, might this be because of our data? And you'd be absolutely correct. Sometimes you can just get some crappy data. In 2016, all of the polls in Wisconsin were crap. That's why no one really ever said Trump could win Wisconsin, because all the polls said he couldn't, but they were all junk. However, this time around the polls were better, because they helped correct for those factors. And this time around, Biden won Wisconsin like the polls suggested. Now, therefore, you could essentially, we're seeing whether or not we can prove the alternative. Because if we prove the alternative is true by showing the null is false, then we're done. Now, you might think, hold on, you got a contradiction here. Can't we just switch the two hypotheses to prove the null? And you'd be right. But the catch is, if you switch them around, you're now assuming a new null. And therefore, the nature of your test is now entirely different, and you're actually conducting an entirely new hypothesis test. And I'll explain this more when we get into our examples in our upcoming lectures. So now, let's get to some examples. I'll do the first one for you, and then you'll do the next two. So, the mean salary of statistics professors, it's at least $70,000. Now, we know that the null hypothesis has to have the equal sign, so these two are immediately out. And it says at least. So at least means greater than or equal to. Therefore, this is our one. And so we have option D. So I'll give you a moment and give you all about a minute or two to do these next two. And with a hint here, notice it never states what the assumption is. And yet, just by knowing the equal sign rule, which you'll recall up here, the equal sign has to be with the null. Just by knowing that, it gives you a lot of help. So I'll give you a minute to do these next two. Okay. Now with here, it says the IQ scores have a standard deviation less than 15. Now, if you're a little bit confused, all of these are statements. So each of these is one of the two hypotheses, and therefore you get the other one by taking the opposite. So we're dealing with a standard deviation. So that means B and D are instantly gone because they're dealing with population means. We don't care about the population means, we care about the standard deviations. That leaves A and C. Now, at this point you might look, they both have equal signs, so you might get stuck. Well, we know that one of our statements is that these students have a standard deviation less than 15. So one of our two has to say sigma is less than 15. That's this one right here. So therefore, we choose option A. Now, number 3. Less than half of all internet users make online purchases. This is a proportion. Therefore, C and D are instantly wrong. In that case, we're left with A and B. Now here we're saying that fewer than 1/2, so less than 1/2. And so here, I'll put less than 15. Less than 1/2 has to be one of our hypotheses. That's this one. So we're left with option A. So that's the thing here. Take your statement that you want to be one of your hypotheses and ask yourself, does this statement include the equal sign? If it does, it has to be the null. If it doesn't, it has to be the alternative. All right, let's move on. Now, let's say we conduct our test, we reject or we fail to reject. There's 4 possibilities. If we fail to reject, the null hypothesis could be true. So we don't reject it when we shouldn't have. So we made the correct decision. With number 2, we failed to reject it even though it was false. So we failed to reject it even though we should have. With 3, we reject it even though it's true. So we reject it even though we shouldn't have. So we made a mistake. And number 4, we reject it when it's false, which means we reject it when we should have rejected it. So if 1 or 4 happens, we made a correct decision. If 2 or 3 happen, we made the wrong decision, so we want to avoid doing 2 or 3. We have definitions for these. Failing to reject the null when it's false is known as a type 2 error. So a type 2 error occurs when we fail to reject the null when, in fact, we should have rejected it. And number 3 is a type 1 error, which occurs when we reject the null even though we shouldn't have. Right here I have a table, and you should put this table in your cheat sheet. This will do a lot to help you. So type 1 is rejecting a true null. Type 2 is accepting a false null. All right, let's move on. So here, just a few examples. So in this case, I'll do the first one, and you'll do the remaining 2. So a criminal trial, what's a type 2 error? Well, we have 4 possibilities. We have a guilty person who we let off. We got a guilty person who we convict, an innocent person who we convict, and an innocent person that we acquit. When we put someone on trial, the assumption is innocent until proven guilty. So our assumption is innocent until proven guilty. Oh, let's try that again. So we can say our null hypothesis is innocent. And our alternative is guilty. So in light of that, we recall from our table that a type 2 error occurs when we fail to reject the null when we should have. So we fail to say that they're guilty, even though they are. So we say that they're innocent, even though they're guilty. So a guilty person is acquitted. That'll be A. So put it another way, type 2, fail to reject H not. So we, put another way, we fail to say they are guilty when they are. So, guilty person is let off the hook. This one, I'll give you about 30 seconds to do these two. These are just definition questions. All right, the first one, the null is not rejected when the alternative is true. That means we didn't reject the null, even though we should have. And that is the definition of a type 2 error. Our other one, we recall our type 1 is that we reject the null, even though it's true. So therefore, C. All right, let's move on. Now let's put these into context. For here, these are all templates, and I recommend that you put this on your cheat sheet, because these give you templates for interpreting an error in the context of the problem. So let's suppose we fail to reject the null, whether or not we know it's true. In this case, our conclusion is that we do not have enough evidence to conclude that we can reject our null hypothesis, that null hypothesis. So in the case of the court example, we would say there is not enough evidence to conclude that we can reject the null hypothesis, that the defendant is guilty. That is why they say not guilty. The courts never say innocent. We say not guilty. Because it's possible you might get some future DNA evidence that confirms that the person is in fact guilty. So type 2 error. Now, if we reject the null, we can say that we reject the null hypothesis that, insert the null. So in fact, there is enough evidence to conclude that our alternative is true. In the case of the court example, we would say we reject the null hypothesis that the defendant is innocent. There is enough evidence to conclude that the defendant is guilty, is true. Now, let's suppose we screw up. We can explain what a screw up would mean. So if we accidentally reject a true null, we might say we reject the null hypothesis that insert null, when in fact the null, that insert null, should not have been rejected. In the court example, that would mean we rejected the null hypothesis that the defendant was innocent, when in fact our null hypothesis that the defendant was innocent should not have been rejected. So that would be convicting an innocent person. Likewise, type 2 error, we fail to reject the null hypothesis, that insert null, when in fact we should have concluded that there was enough evidence to conclude that our alternative is true. In the case of the court example, we would say we fail to reject the null hypothesis that the defendant is innocent, when in fact we should have concluded that there was enough evidence to conclude that the defendant being guilty is true. So for this, I recommend put this on your cheat sheet. It's kind of filling in the blanks, basically. So, in our example, we have the ones from earlier. As practice, I want you to explain what a type 1 error would mean in the context of each problem, and then explain what a type 2 error would mean in the context of each problem. So here, I'll give you about a minute to do each of these. You should use the box from above. And here I'll scroll up just for a moment. Here's the box. Give you a few seconds to snip it. All right. Give you a minute to work on this. Okay, let's go ahead and go over. So we recall a type 1 is rejecting it when we shouldn't have. So in the case of the Colorado example, we would say that we rejected the null hypothesis that Colorado is a battleground state when, in fact, we should not have rejected this null hypothesis that Colorado is a battleground state. In the example of the constructors, we rejected the null hypothesis that the instructor was not giving out too low of grades relative to the rest of the instructors, when, in fact, we should not have rejected this null hypothesis that the instructor was not giving out too low of grades relative to the rest of the instructors. Okay? Now our type 2 errors. A type 2 is failing to reject the null when in fact we should have. So in this case, our type 2 error, for the Colorado example, we failed to reject the null hypothesis that Colorado is a battleground state when in fact we should have rejected it in favor of the alternative hypothesis that Colorado is not a battleground state. In the case of the teaching, we would say that we failed to reject the null hypothesis that the instructor was not giving out too low of grades relative to the rest of the instructors when, in fact, we should have rejected it in favor of the alternative hypothesis that the instructor is giving out too low of grades relative to the rest of the instructors. Oh, my text just went away. I'll just retype it. So we rejected null hypothesis that Colorado is a battleground state when in fact we should not have. There we go. So in summary, type 1, rejecting when we shouldn't. Type 2, failing to reject when we should. Okay? So, now a natural question is, when do we reject? We have to set some threshold for where we say, I'm convinced, we reject. Now, if we set the threshold for rejection as alpha, then that means the odds of screwing up will be alpha. So therefore, we can say that alpha will be the chance that we screw up and also the threshold. And the reason why, because you recall with confidence intervals, alpha was the probability of our true mean or proportion being outside of the interval. So it's the probability of screwing up. Now, you might ask, doesn't this probability of screwing up also include the chances of failing to reject the null when we should have? However, if we failed to reject this null when we should have, we were either extremely unlucky or had a bad sample. Well, we can correct for the unlucky part simply by having a very low value of alpha. If our value of alpha is 0.01, then we only have a 1% chance of getting extremely unlucky. So that low alpha takes care of that. So in this case, the only time we should be screwing up is if we have a bad sample. Now, on the other hand, what happens if we fail to reject when we should have? Well, like before, we get a very bad sample. But if we have a really bad sample, we were going to screw up no matter what. In Wisconsin in 2016, everyone, whether people said, some people said Trump was going to win Wisconsin by 10. That was wrong. Everyone's wrong because the data screwed up. And so in this case, all we have to do is to correct our sample. So therefore, the type 1 error is what we care most about. And therefore, this is another reason why we say fail to reject. By saying this, we recognize we had a chance of getting a crappy sample, which therefore mitigates most of the ramifications of a type 2 error. So we hit two birds with one stone. Therefore, and this is something you need to have on your cheat sheet, I'm going to assess you on it. Alpha is the probability of committing a type 1 error. So if alpha is 1%, then we have a 1% chance of making a type 1 error. In the case of the Colorado example, we could say that there is a 1% chance that we reject the null that Colorado is a battleground when, in fact, it is. Okay? Let's move on. Now, we have the other end. The power of a test is the chance that we correctly reject a false null. So, technically speaking, the probability of a type 2 error is 1 minus the power. But in this course, I'm not going to ask you to compute that probability. You'll only deal with probabilities of a type 1 error. But I'm giving you this definition so that you have it for the web work and just to be in the know. So, like I said, if alpha is our probability of making a type 1 error, then it's our threshold. So now, let's suppose we conduct a hypothesis test, and we get the probability of the event happening by random chance. Because if our sample is not screwed up, then one of two things is going to happen if the null is false. Let's suppose the null is false. If the null is false, we could still fail to reject it just by sheer chance. And so the idea of getting a p-value is to assess the probability of getting the result that we got by random chance. That is, if the null is true, what were the odds of getting a result this far away from the null by sheer chance? And that is called the p-value. If this p-value is below alpha, then we reject the null because we're saying the odds of this happening by random chance are so low that we can safely say it didn't happen by random chance. To give you an idea of that, think of it like flipping a coin. If you flip a coin twice and you get heads twice in a row, you can pretty reasonably assume that could have happened by random chance. If you flip a coin 4 times in a row and get 4 heads, we're starting to push it, but that could have still happened by random chance. On the other hand, if you flip your coin 20 times and it comes up heads 20 times, the odds of getting heads 20 times in a row by random chance is 1/2 to the power of 20. That is so small that we can pretty safely conclude this is not a fair coin. That's the idea behind p-values. Now notice you don't need alpha to compute the p-value. We decide our threshold alpha beforehand. We compute the p-value from the statistics, and in the remaining lectures, we'll be computing these p-values, and I'll show you how to compute them. But for now, I wanted to introduce you to the concept of it. Now, let's suppose our value of alpha is 5%. If we get a p-value of 0.5%, we'll reject the null. If we drop the value of alpha to 1%, we'll still reject it because the p-value is that small. In that case, we say this is a very, very powerful p-value. It's going to reject for pretty much every null. On the other hand, let's suppose we have a p-value of 7.5%. If it's 7.5%, we would reject the null if alpha was 10%, but we wouldn't reject it if alpha was 5%, because 7.5% is less than 10%, but it's not less than 5%. I'll give you an example so you understand what I mean. So let's suppose we got a professor who wants to refute the claim that the average student spends 3 hours studying. In this case, we're refuting it, so it's the null. 3 hours studying, mu is equal to 3. So this is out, and this is out. Now, in this case, the alternative is the opposite of the null, so that's the correct H1, so this is D. So now, which of the following p-values will lead us to reject the null if alpha is 0.05? So we have alpha is equal to 0.05, and we need p-value to be less than 0.05. 0.15 isn't, out. 0.1, out. 0.055, close, not enough, out. But 0.025 is less than 0.05, so this p-value will lead us to reject our null in favor of the alternative. So here, I got a couple of practice ones here. I'll give you a minute to work on these. As a note, our p-value comes from our statistics. You know, we have our sample means, our sample standard deviation, so our p-value comes from those test statistics. So actually, I just gave you the answer that this one is C. But regardless, go ahead and spend next minute doing the other two. All right, I'm going to start with one on the right. The power of a test is the probability of computing a type 2 error. And we recall our type 2 error, you recall that from up here, is that we correctly reject a false null. So therefore, we fail to reject a false null. You'll recall down here, type 2, failing to reject a false null. So let's go back over here. Fail to reject our false null. Our other one, so we have this hypothesis. We don't reject it at 10% significance. So we have alpha is equal to 0.1. We didn't reject it, so our p-value was greater than 0.1. If it's greater than 0.1, then that means we're not going to reject it at 0.05, so this is out. We're not going to reject it at 0.025, so this is out. Now, if this p-value is 0.15, we wouldn't reject it at 0.15, but we would reject it at 0.2. So this is out. But if it's 0.15, we won't reject it at 0.05. So this is correct. Now, a natural question you might ask yourself is, Professor Bailey, are you saying we can determine the outcome of a test just by changing the value of alpha? You'd be correct. This is why the alpha, you always set your value of alpha before you do the test. Usually we do 1% or 5% or maybe 0.01%. But for all the problems, I will give you the value of alpha. Or you'll be given the confidence and have to get alpha from the confidence. Okay? So, this p-value came from a test statistic. Let's actually talk about this test statistic. Our test statistic for all of our upcoming lectures will always be a z-score or a t-score. You recall the z-scores came from the t-tables, and the the z-scores came from the z-tables, and the t-scores came from the t-tables. Now, let's suppose you found your score. Getting the probability, p-value means probability, associated with that score is the same as before. Once you have a score, you find the probability from the table. So for example, if we have a z-score, let's suppose we have z is equal to negative 0.5, our p-value is 0.3085. So once you get your score, process is the same as it has been. Now, technically, you can take your p-value and convert it into a critical value. And the critical value is our z or t score, where if the magnitude of our test statistic is greater than that magnitude, we reject it. So, for example, suppose we have p-value is equal to, or even better, we have our alpha. Let's suppose we want our level of significance to be 0.4%. In that case, that's 0.004. We find that in our table right here. So we have z is negative 2.65. So if our test statistic is lower than negative 2.675, then we're going to reject. If it isn't, then we fail to reject. Now, technically, our test can be one-tailed or two-tailed. You might ask, what does one-tailed or two-tailed even mean? Here's what it means. Let's suppose we're asking if it's equal to. Well, it could be not equal to. Well, that might be over here, or that might be over here. In this case, it could be in either tail, so it is two-tailed. On the other hand, if we're dealing with less than or equal to, let me move that over a little bit. If we're dealing with less than or equal to, then if we reject it, it's got to be over here, so it's one-tailed. Now you might ask, okay, that's nice. What's the point of that? This test statistic, this p-value, is affected by whether or not it's one-tailed or two-tailed. And here's why. If it's two-tailed, we just got to be out in here. Doesn't matter which one we're in, as long as we're in one of these two, we're good to go. So that means our cutoff has to be one of these. Because of symmetry, that means this is going to be at alpha over 2. Because the two probabilities have to add up to alpha. These two have to be alpha. Whereas with here, this whole thing is alpha, so we get it at alpha. As an example, let's suppose our level of significance is 0.05 and our two-tailed z-score is negative 2.58. Is this one-tailed or two-tailed? It's two-tailed because it tells us it's two-tailed. Now, what is our p-value associated with that z-score? Well, we have negative 2.58. So, negative 2.5, negative 0.08, or 0.08. See where they line up? 0.0049. So 0.0049. Now, should we reject the null? We reject the null if our p-value is below the level of significance. This, so 0.0049, is less than 0.05, so we reject. Now, let's suppose our level of significance was 0.01. Would we still reject? The answer is yes. And the reason why is because 0.0049 is still less than 0.01. So we see we have a really strong p-value here. And we'll get into some really concrete examples of this in the upcoming lectures. But this is meant to explain some concepts of it. Okay? So, the general formatting of a hypothesis test is this. We all start off the same way. We have to identify our hypotheses, and we got to state our value of alpha. And then we have to compute our test statistic. And we'll compute those test statistics in the upcoming lectures. Now, if we're doing the p-value approach, we have to use one of our tables and convert this test statistic into a p-value. Then we compare the p to the alpha and decide whether or not to reject. If we're going to use the critical value approach, we turn our alpha into a cutoff score with the tables. So we just work backwards. And then we compare the statistic with the cutoff value and determine whether or not to reject from there. And it's going to end in the same way. Based off of our rejection or non-rejection, we should interpret it in the context of the problem. And again, you can use that interpretation from over here. When I gave you these boxes, you would use one of these two. Okay? Now, technically, we can do confidence intervals. So we would just construct a confidence interval like Unit 3. And so, if our sample mean is outside the interval, we reject, otherwise fail to reject. So technically, you've actually already done most of the work for many of these hypotheses tests. You just haven't done the hypotheses themselves. This should be on your cheat sheet. All right, we will work with our hard numbers, and we're going to spend all of our remaining lectures just doing a bunch of hypothesis tests, because it's a decent bit of math, it's a lot of interpretation, and I think it's important that I give you as many examples as possible to work through when doing them. Anyways, that's about all we got. So, I'll see y'all soon. Bye-bye. Enjoy the rest of your evening.